we are going to take today and he will talk about marginalized space of
Instantons.
Sorry.
Asymptotically constant in manifolds. It's a mouthful. And so thank you for inviting me. This is my first talk outside NTU or NCPS in the top, outside Taipei. So I just started my postdoc at NCPS and I came from University of Leeds in UK. I also did my PhD and then worked there a bit after that. And so I'm a gauge theorist. I do gauge theory, which means in lower dimensions, that means studying objects like instantons, monopoles, Yang-Mills equations and things like that. And I made things worse, and I'm like, I'm gonna do this in higher dimensions 7 and 8. That also has a lot of physics origin. So before I start talking about the gauge theory aspect and my work and things like that, first I will of course focus on this first and then this first. First, let's get to know the manifolds. What are the geometric objects that we will do the gauge theory on. So to talk about the manifolds, spin 7 manifolds, I should better start part 1. Start with the very basic notion of holonomy. So, very quickly, if I have a Riemannian manifold, simply connected, oriented, non-locally symmetric and irreducible, then the all possible holonomy groups of the manifold are UN, SUN, SPN, SPN.SP1, G2 and spin 7. And for those holonomy groups to occur, the dimension of the manifold has to be real dimension 2n, 2n, 4n, 4n and 7 and 8. So just to recap, holonomy groups means you consider the group of parallel transports along a closed loop, and then of course they will I started my manifold to be oriented. So these holonomy groups will be subgroups of SON in the dimension of the manifold, and then this classification was by Beje in 1964, if I remember correctly. And surprisingly, not surprisingly, the holonomy groups, so these are holonomy reductions from the Riemannian holonomy group SON, and these groups are in one-to-one correspondence with geometric structure. So Riemannian structure, you have the metric that will give you the orthonormality notion, and that's why the holonomy group is SON. Here UN the manifold will be a scalar manifold. For SUN it will be Calabi-Yau. SPN hyperscalar. SPN dot SP1 will be quaternion scalar, and these are, because they are very special, the structures are also called G2 and C. These are so that's special structure, and these are called manifolds. The manifolds have these holonomic groups, have these geometric properties. They are called manifolds with special holonomy. Now these two, as you can see, they are exceptional among the special holonomic manifolds. They are called manifolds with exceptional holonomy. So they are not just special, they are exceptional. And that's the focus of these manifolds are the focus of today's talk. We will use actually both of them to make sense of this particular manifolds called asymptotically conical N7 manifolds. So I'm going to do this by comparing with SU3 structure. So SU3 structure, from here you can clearly see that means you consider Calabi-Yau threefold, and that's a relatively well-known object among geometers. So I'm going to start from there, and then we'll define those by comparing them with the SU3 structure. So SU3 I'll start a 6-dimensional Riemannian manifold. I'll have a fundamental 2 form, small omega, and a holomorphic 3-0 form, capital omega. Right? And then my manifold will be Calabi-Yau if and only if these are integrable. And of course there are some compatibility conditions which I don't care about it now. So we are going to focus on this condition that these holomorphic 3 form and the simplistic 2 form are integrable, which means these two conditions, and they are equivalent. Nabla omega equals 0 is same thing as d omega equals 0. This is the integrability condition of the SU3 structure. So these constitute the SU3 structure, and the integrability means the holonomy of the metric is actually contained in the group SU3. Right? So the natural question is, okay, can it happen that the holonomy group is not contained in SU3, so it's not integrable, right? There are manifolds which are of course not Calabi-Yau. The SU3 structures are not integrable, but they are still important. Let's look at an interesting example of that, or rather interesting manifold, nearly scalar manifold. So here the condition is your d omega will be 3 times the imaginary of the holomorphic capital omega, and the d of real part of omega should be 2 omega square. So as you can clearly see that d omega is non-zero, but there's still some control, coming from there's still some condition between the two structures, small omega and capital omega. This is also known as in the old literature by Gray manifold. So here the structure is non-integrable, and you know the holonomy group is not contained in SU3, but the SU3 structure is still there. It's the small omega and capital omega, right? Both of these are actually important, and you can clearly see how the geometric structure, the Calabi-Yau structure, comes from a differential form. So I'm gonna introduce the G2 and spin 7 manifold, okay, at least for G2 manifold, similarly by starting from a 7-dimensional Riemannian manifold and a 3 form on it. So locally, in a local orthonormal frame, I can write this 3 form as E. Okay, let's denote a notation. Let's fix a notation. EIJK means EI with EJ with EJ. Clearly a 3 form. So I can write this 3 form phi as E127 plus E347 plus E567 plus E145 plus E136 plus E235 minus E246. And of course, this is a 4 form. I also have a 3 form. I also have a 4 form by taking the Hodge star, which I'm gonna denote by psi. That's a 4 form. That dimension is 7. Now the definition is, I'll call this manifold sigma 7 G2 manifold if the left-shooter connection applied to the 3 form is 0. Alternatively, there is the same definition. D phi equals 0 and D psi equals 0. Now that you have, I have the Calabi-Yau case on the left-hand side, you should be convinced that that's a very convincing way to define a geometric structure on a manifold. That 3 form phi is called the G2 structure, just like we called this omega and capital omega the SU, the Calabi-Yau structure, or SU3 structure. So altogether, when I'll mention a G2 manifold, I'll just say sigma G phi. That's my G2 manifold with the G2 structure, small phi. Now here, that's an integrable G2 structure, just like we had here for Calabi-Yau. Now what about this? Exactly like this, I can have a weaker notion where the holonomic group is not contained in G2, the G2 structure is not integrable. We'll call it just like that, nearly G2 manifold. And of course that means clearly you can see now D phi, we shouldn't expect them to be 0. In fact, the condition is D phi equals 4 psi. This is just a scaling, don't worry about that. So that's nearly G2 manifold. Clearly phi is not closed, which means you don't have integrability, but phi is co-closed, which means psi is closed, because if you apply D on that condition, D2 phi equals 0, so D psi equals 0. So these are the integrable structures, these are the not integrable structures, but still important. So for the integrable structures, the holonomic containing the holonomic group, holonomic group from that list, for others don't. So that's the G2 manifold. Now why the word G2? If you have done some Lie group Lie algebras, G2, the Lie algebra G2, so in the Dynkin diagram, if you remember this, it's in the Dynkin classification. So the reason is the Lie group G2, whose Lie algebra is that, is the stabilizer group of this 3 form. So that's and using that you can also prove that the holonomy is also contained in the Lie group G2. So now I want to define the spin 7 manifold, and I can do exactly the same. I can write down a 4 form and then exactly the same thing will work. But I'm going to do it a bit differently. I'm going to take the help of the lower dimensional object. Ultimately it's the same thing. I just want to show you another very nice aspect of or rather relations between these geometric structures. consider a simple example. R6 considered as a Calabi-Yau manifold. So your that fundamental true form, I can write it as E1 with E2 plus E3 with E4 plus E5 with E6, and the holomorphic 3 form, I can write it as E1 plus I E2 with E3 plus I E4 with E5 plus I E6. That's the choice. Now, so you can see R6 cross R is R7, and I'll have a G2 manifold on my R7 will be a G2 manifold with the G2 structure phi 0, which I'm gonna define using the already existing Calabi-Yau structure. So I'll define it as phi 0 as omega 0 with E7 plus imaginary part of omega 0. So what's E7? I have the basis of R6 to be E1 up to E6, which I used here. I'll consider a cylinder over it. So that's R6, and the radial direction I'll pick the coordinate to be E7. So basically, this means if you consider cylinder over a Calabi-Yau manifold, you'll end up with a G2 manifold. So I'm gonna simply use this to define my spin 7 manifold very simply. So I'm gonna do the same on R6. On R8 by considering R8 to be R7 cross R. I'll define a 4 form on it. By this 4 form is E0 with phi 0 plus phi 0. So that's my phi 0, and of course the star of phi 0 is like first star applied on it. Now of course like that I have my G2 manifold here R7, and in the radial direction I'll choose a coordinate E. So this is a 4 form. On R8, right? So in general, I'll start with an 8-dimensional manifold, and I'll define a 4 form, which again you can start with this expression and can easily write down the corresponding phi's in terms of EI, and we'll call it spin 7 manifold if the Levi-Civita connection on this 4 form is 0, which is the same thing as saying D on this 4 form is 0. That's the definition of a spin 7 manifold. And this means the holonomy will be contained in the Lie group spin 7 and so on. So that's the kind of a review of the basic notions of G2 and spin 7 manifold. Any questions so far? Now I'm going to define actually this manifold, which is asymptotically conical manifold, but I already kind of set up the background, so I can define that pretty easily. Any questions so far?
Does that mean that for all spin 7 manifold it has to be topological out 8? Does it have to be Euclidean space in topology? Is it?
No. It's just I took the help of this to define the form. Locally, I mean a manifold, you can define the charts, and you can define you have the local orthonormal basis of R8, and by then you can use that to write a local orthonormal write the 4 form on your manifold in the local orthonormal basis. So I'm just taking help of Rn to write down the expression for the differential form, and using it as a simplest example.
I see. So in general, for spin 7 manifold, doesn't have to be split as R times a 7-dimensional
No,
manifold, satisfying that kind of structure.
definitely not. But the point is, if you go the other way, you start with a G2 manifold and consider a cylinder over it, you know that will be a spin 7 manifold. So don't go down and consider all spin 7 manifolds to be a product manifold, but the other way is definitely true. You start with a product manifold, that way the spin 7 structure on that product, rather I should call on that cylinder, is the obvious one.
I see. Thank you so much.
I'm glad we took care of that easily. I just use R8 to write the expression of these forms in the local orthonormal basis. That's it. Now I'm going to talk about the asymptotically conical manifolds. So you just saw that if we construct a cylinder on a Calabi-Yau or G2 manifold, it will give me the one-dimensional higher manifold with the integrable structure. But now we are going to consider a cone rather than a cylinder. And what will happen there, you had G2, you got spin 7. For cylinder, if you start with a G2, you can easily show that the cone you end up with, the spin 7 structure cannot be integrable. You need to start with this non-integrable nearly G2 in order to get the integral structure. That should be very clear from this expression. If you apply the condition that d phi equals 0 on this and simplify and calculate, it will directly spit out that expression d phi equals 4 and vice versa, and conversely. So that's the fun with it, fun about the cone rather than the cylinder. You need to start with the non-integrable structure in order to get integrability on top. And so let's quickly write down the expression. So I have the 7 manifold. My cone is nothing but 0 infinity cross sigma. The conical metric is dr square plus r square g sigma. Right? That's the conical metric. And then the spin 7 structure is r cubed dr with phi plus r to the power 4 psi. And then you can show that this is 0 if and only if d phi equals 4 psi. So that's the cone. But there's a problem working with these manifolds. There's a singularity, the conical singularity. So the idea of asymptotically conical manifold, I'm going to draw the picture over here because we need to refer back to it a lot of times. So I have the cone, this goes on forever. I have the G2 manifold, I have the projection pi. Now what I do, this is my radial direction, 0 infinity. What I do, I start with a complete manifold X. I cut out a compact set from it, and here I cut out a little the lower part of my cone. So this part, what I am left with is R infinity cross sigma. Whereas here I am left with x minus k. And that's a diffeomorphism. So that's my condition. I picked the manifold X in such a way that when I cut out the compact set part, it will be diffeomorphic to the cone with the lower part cut out as well. Alternatively, you can think of it as you kind of resolve that singularity by adding something to the cone, where the metric can change. So let's so that's my manifold, but there's already a spin 7 structure here. There's a metric here. Now here we have another spin 7 structure and a metric, and these two sets should be as very close to each other in the sense that they should satisfy an asymptotic relation. That's how this asymptotically conical term comes into play. So let's define it rigorously. I have a manifold. I start with an 8-dimensional non-compact spin 7 manifold. I'll call X asymptotically conical with rate mu less than 0. This is very important. If there exists a compact set K, a compact nearly G2 manifold sigma R greater than 1 and diffeomorphism H from capital R sigma infinity cross sigma to x minus k, such that if you pull back that fourth form on this upper part of that manifold x minus k to the cone and compare with the existing fourth form on the cone, and you can you take the derivative, that should be of order r to the power mu minus k and r. That's your asymptotic relation. Okay, this needs to be applied on Rp, a point where P is in sigma and J of course positive integer and R is somewhere in that line. So the idea is the geometry of this should be very close to the geometry of the cone, and that's the asymptotic condition that it should satisfy. A bit involving the definition. Important thing is this rate, because when in practice when you want to calculate these, and then the rate will be important information to do analysis on these manifolds, which we'll see pretty soon. Okay, so what are the examples? The easiest example, which I'm gonna write down right now, is R8. You start with the round 7 sphere. You consider the cone over it, which means use the conical metric, and then that conical singularity you just add one single point, and that's R8. So there, this order is okay. Ultimately, a lot of ultimately any new will work for that one, because you are just adding one more point to it. That's actually the best example and most important example for physicists, because they do care about Euclidean space a lot, and most of their results are on Euclidean space. Another example, it's a bit complicated. So this is the round sphere. In dimension 7 there's another kind of sphere which is called a squashed sphere. So in terms of the homogeneous spaces, you can write it as sp2 cosine sp1 cross sp1 cosine sp1 square. So basically what you do, if you consider the Hopf vibration of S7 into S4 and S3, you squash the metric on the 3 part, yes, and then that's your, so you change the scale of that 3 part and you get the squash sphere. So on this, if you consider the cone and then you attach a fourth sphere to it, that's a spin 7 manifold, the negative spinor bundle of over S4. This thing was well known long before, but I mean this is a very trivial one. This is called the Bryant-Salomon. I'm going to write the whole thing. Bryant-Salomon manifold. So Bryant and Salomon actually wrote down a lot of non-compact complete spin 7 manifolds, as well as G2 manifolds, where the holonomy is it's a full holonomy. The holonomy of R8 is just a point. That's a very trivial example. Whereas the Bryant-Salomon manifold is a proper example of a full holonomy complex spin 7 manifold. Right, so far that's the best one. People are writing down few other asymptotically conical metrics, but they are still far from well understood. Now, so you saw these two examples of spin 7 manifold, asymptotically conical spin 7 manifold. Let's now I need to do analysis on it. I need to so gauge theory works with PDE. So you have PDEs on these manifolds. You need to understand at least some sort of analysis like Sobolev theory. Now you have done Sobolev theory. Well, like these are non-compact manifolds. How dare you talk about Sobolev theory on a non-compact manifold? There's a different analysis which I'm going to mention it right now. It may and the motivation will be clear later on. It's called and it has nothing to do with gauge theory or even special holonomy. It will work on any asymptotically conical manifold. If you have non-compact manifolds you want to do analysis on, this will work. So, by the way, just a comment, this cylinder construction and the cone construction, and this coming from the Calabi-Yau to G2 to spin 7, these are directly related to something called flux compactification in string theory. So they need to consider first of all 10-dimensional theory where you have the Calabi-Yau 6-fold times your space-time, and suddenly they are like, okay, we like 11-dimensional theory now. How do you jump from 10 to 11? You precisely consider the cylinder or cone on your Calabi-Yau manifold and go to G2 manifold, and then you can do M theory in 11 dimensions. These are the way you can jump up. So that's the physics side of things, why this G2 and spin manifold will come up in the physics side of story. Okay, a bit of analysis now. Locker-Machman analysis. I'll be very brief. So suppose I have a vector bundle on my spin 7 manifold. If you have have not seen vector bundle, just think of tangent bundle where the fiber doesn't have to match up the dimension of your manifold. So if you have n-dimensional manifold, the fiber of your bundle doesn't have to be anything. That's the general notion of your tangent bundle. You can consider it to be the vector bundle, and very similarly you can consider a connection on it. Again, if you haven't seen connection on the vector bundle, you can just think of a generalization of your lattice theta connection, which is compatible with the metric. So now, suppose you have a compactly supported smooth section of your bundle. You need to define a Sobolev norm. So I'm gonna define the Sobolev norm of this section as WKP nu E. See, I told you the nu, the rate, will come in handy. WKP nu E equals summation A equals 0 to K rho to the power minus mu plus J naturalization to the power P rho minus 8 d whole. So now those who have seen Sobolev norm, if you compare it, you are like, you have almost the same except for this part and this part. Exactly the part which involves this mysterious rho. Right? If you remove that, that's your usual Sobolev norm. So let me define what this rho is. Again, looking at this picture, things should be pretty clear. See, in that picture, the main problem is this. The upper part is just same as the cone. The lower part, you have the compact set. So when you talk about the radial direction for this, that's not that changes. For the upper part, it's the usual radial coordinate as your cone, but for lower part, it's different. So the way we define this rho, we call it the radius function. So rho x is your usual r when x is 8 rp or r in 2r infinity. High enough, it's the same function. When it's in that compact set, it will be 1. And for the middle, r to 2r, I started with 2r. When it's in between that, I'll just smoothly interpolate it starting from r to 1. And that's your radius function which appears there. Here this minus 8 is clearly coming from the dimension of your manifold. And that's the Sobolev norm. We'll call it the weighted Sobolev norm, where the weight is new. The weight will come from the manifold. The manifold will tell you which kind of weight you should work with, or rather the range of weight. So these are the complicated manifold, but still not complicated because you can see the simplest example in there. The main point of this elaborate construction is when you actually need to work with these manifolds, work on the gauge theory and things like that. You need to talk about like Sobolev norm or index theory, a lot of analytic tools that are only defined for compact manifolds. But you need to do it for R8, which is highly non-compact. So you need proper analytic support, which considering R8 as asymptotically conical manifolds will give it to you. And so that's the first part of the talk. Don't worry, the two other parts are smaller. This was the main important one. Knowing the manifold and the analytic tools for which you can do a lot of stuff on these exceptional holonomic manifolds. I mean, writing down examples is pretty easy for non-compact manifolds. Doing the analysis is the hard part. For compact manifolds, writing down the examples are extremely hard for these higher order manifolds. You need to use a lot of algebraic geometric techniques, like you start with the orbifold, resolve singularities, and do a lot of analysis to find compact examples. But then analysis is pretty easy. So now I'm gonna talk about gauge theory in the original 4-dimensional setup. So gauge theory means the study of connection. You already saw Levis-Beta connection. I wrote down a connection on a vector bundle as well. Whatever gauge theory means to physicists, it actually, you can, if you compare them with the geometric objects, you will see that just a connection on the bundle. So let's think about what kind of things these are. Suppose I start with a compact oriented manifold. I consider a compact semi-simple Lie group. So there's a notion of principal bundle, which means you have the manifold, you have the fiber is your Lie group. So at each point, when you take a point x and consider pi inverse x, suddenly that's your Lie group. For example, for tangent spaces, you know that will be your TPM. If you fix a point on your manifold, you look at the fiber, that's your tangent space. Here, that will be your Lie group. A lot of group actions involved, which I'm not gonna talk about now. Now, from this principal bundle, they are called principal bundles. Your fiber is a Lie group. There are notions of vector bundles, where of course your tangent bundle is an example of the vector bundle, because your fiber is a vector space. So that's the idea. So from this principal bundle, you can actually easily cook up a vector bundle. So what's the vector space you can think of coming from your Lie group? It's clearly the Lie algebra. So, or rather the adjoint representation of your Lie group. So that's called the adjoint bundle, where you consider the vector bundle, which I'm going to write it as GP on your manifold, where the fiber is the Lie algebra. And the nice thing is the notion of connection and curvatures on your Lie group, on your vector bundle corresponds nicely to vector connection and curvature on your Lie algebra. So there's a completely different way to define connection and curvature on principal bundles, but because you already seen connection and curvature on vector bundles, in particular, if not at least for tangent bundles, it's the very same thing. In particular, so I'm going to consider a connection A on my principal bundle. You can just think of it on the vector bundle. Then the curvature of this connection, FA, you can write it as dA plus half A. So maybe you have seen that kind of form in Riemannian geometry as well. This thing means, so that's a two form, connections are one form and curvatures are two form, right? So this A means when they are applied on a vector field xy, that's actually the Lie bracket of AX and AY. Clearly this Lie bracket is coming from your Lie group. So if you start with a Lie group which is abelian, this term will be 0. So in particular, from this I'm going to define the covariant derivative as dA subscript A is d plus half A dot. So clearly you can see in this format your curvature is the covariant derivative of your connection. And there's something called the gauge group. So you have your bundle. Gauge group is nothing but the automorphism group of your bundle. So it will preserve the fiber, and then it will take your connection to another connection, and that's called applying an element of a connection is called, an element here is called gauge transformation. So two connections are gauge equivalent if you can just apply a gauge transformation on one and get the other. So I'm gonna define the gauge group. So you have the set of all automorphisms. So I'm gonna define denote this gauge group as like this notation G, curly, right? So these are basically bundle theory, the theory of vector bundles and principal bundles. The gauge theory comes into play where in physics when you write down the Lagrangian of some physical quantity, and then you turns out those objects actually are nothing but objects involving the connection and curvature of your bundle. So you have heard of Yang-Mills theory. Okay, another notation. I'm gonna denote AP to be the set of all connections on your bundle P. So certainly when Yang and Mills was working on weak forces, strong forces of particle physics, they wrote down the Yang-Mills Lagrangian, which turned out to be a map from this set AP to a 4 form, which means if you give it a connection, it will give you a 4 form. This is nothing but non-vector square. Remember, your curvature is your connection is a 2 form, and curvature is connection is in 1 form and curvature is 2 form. So FA with hot star FA in dimension 4, hot star of 2 form is again 2 form. So this is 2 form with 2 form is a 4 form. So basically you are giving it a connection and getting a 4 form. That's your Yang-Mills Lagrangian, and then Yang-Mills functional is just you integrate it over your manifold. So this is so you get the action by integrating your Lagrangian. And when you have a functional, it makes sense to talk about the critical points of the functional. It's that's how the variational principle people think about it. Whenever they see a functional, they're like, what are the critical points? And it's important to know the critical points. So you can prove that by using Euler-Lagrange on this Lagrangian, or rather on this functional, that the critical A, remember your connections are the critical point, has to be the critical point. A is a critical point if and only if it satisfies this equation, dA star equals this. So you had dA there. dA star is the formal adjoint of dA, which you can write like this: minus hot star dA hot star. So dA increases your form by 1, dA star decreases your form by 1, which you can clearly see from that. Now this equation is the Yang-Mills equation. Right? That equation is called Yang-Mills equation, where any connection on your bundle A where the curvature satisfies this equation are the critical points of this Yang-Mills function. Now there's a very famous identity which is called Bianchi identity. Again, it works very similarly to what you have seen in the Riemann geometry. You apply the covariant derivative on your curvature, it should be 0. So that's also another. Now in physics, the reason Yang and Mills started working on this, of course we are talking about principal bundles. You have the Lie group G. What are they? If you consider your Lie group G to be U1, then this, what I have written down here, is exactly your electromagnetism, Maxwell's electromagnetism theory. You can write the Maxwell's equation, the 4 of them, just using these 2 equations. If you simplify them and remember there are certain things in you have the electric field and magnetic field, and you can write the potentials using them, the scalar potential and vector potential. They are precisely can be written using this curvature. Well, no, the scalar potential and vector potential are precisely your connection, and then your field strength is your curvature. So basically these 2 equations, take my word for it, is your electromagnetism, Maxwell's equation. Now what Yang and Mills did, they considered SU2 and SU3, and that they claimed, which were definitely true, it described the weak and strong forces in the universe. So electromagnetism, weak force, strong force, these are all the force that will describe the particle physics, namely the standard model. So U1 cross you may hear about things like U1 cross SU2 cross SU3 is the standard model. This is why. So the Yang-Mills equation, you consider particular Lie group G to be U1, SU2 and SU3, and the physics they will describe is precisely the physics of standard model. Now I still haven't managed to talk about instantons, which is in my in the title of my talk, but that's a pretty quick definition. The Yang-Mills equation is dA star equals 0. The instantons are particular solutions of Yang-Mills, a particular connection A which satisfies hot star of Fa equals plus minus Fa. So that's your instanton equation. When people talk about instanton equation, they mean this. Now I just claim that they solve the Yang-Mills equation. How? It's a one-liner. So you have hot star of Fa. Okay. You want to apply that. This should be 0. If your connection is satisfies Yang-Mills, this should be 0. In there, dA star Fa means minus star dA star Fa equals 0. But Fa, star Fa is plus minus Fa. So this is nothing but plus minus star dA Fa. Let's not write 0 here. Yeah, star dA Fa. But the Bianchi identity already tells you that star dA Fa equals 0. You can clearly see the instanton equation will imply the Yang-Mills equation. Now you can prove using Chern classes and some characteristic class theory that these are not just critical points, these are the absolute minimizers of the Yang-Mills function. Right, I'm gonna keep this here, and now I'll ask, okay, so I definitely wrote down the instanton equation. What are the moduli spaces? That's pretty easy. The moduli spaces of instanton are nothing but you have the set of all connections or all instantons and you quotient it by the gauge group. So infinite dimensional manifolds still quotiented by infinite dimensional manifold, and somehow because of that action you could come end up with something finite dimensional. So that's the moduli space of instanton. Now in the last couple of minutes I'm gonna say that I talked about the 7 and 8 dimensional G2 and spin 7 manifolds, and I finally talked about this instantons in dimension 4. I want to write down instantons in dimension 7 and 8, which means I have to write down instanton equations in those dimensions. This equation definitely will not work. If you take Hodgster of a 2 form in 7 or 8 dimensions, you will end up with something 5 or 6 forms. But then you suddenly remember, okay, I do have certain differential forms. Those small phi have 3 forms for G2 structures and a capital phi for 4 form in spin 7 structures. Looking at this equation makes sense for any dimension. But I'm gonna write down something for a G2 manifold. I have the curvature and I want to get the curvature back. I'm gonna weight it with the 3 form, the G2 structure. 3 with 2, 5, Hodgster of 5 in 7 is 2. This equation makes sense. That's my new instanton equation in dimension 7 for G2 manifolds. And for spin 7, I'm going to do the same. I'm going to utilize the 4 form, and you can clearly see the dimensionally it makes perfect sense. So these are the instanton equations which you will find in many supergravity papers around like 1980s, written in very local coordinates. And then mathematically like that in the work of Simon Donaldson, Dominic Joyce, the mathematicians around 1990. And so on these spin 7 manifolds you can similarly talk about the moduli space. Take all the connections that satisfy this equation, consider that set, quotiented by gauge group, and that's your moduli space. And so now I'm gonna write down the main result. As you can see, I had 2 very popular spin 7 manifolds. I looked at the instantons on them. I considered the moduli space, and I used the asymptotically conical manifold techniques and the Lockhart-McEwen analysis and some index theory. Because it's dimensional 8, I use something like analytical tools from Dirac operator spin geometry to study the deformation of the instanton, and a lot of analysis. But the main result is when you have R8, there was a famous instanton written on this manifold by 4 physicists, Fraley, Nuit, Fubini and Nicolai in 1984. You just need to know their connection. You can write down their connection using the local coordinates. The result is moduli space of that instanton is a smooth manifold, assuming it's unobstructed. Again, you don't need to know about that. is a smooth manifold of dimension 1 and 8 when that rate, remember I wrote down the rate, is between -1 and between -1 and 2. So again, why this thing? Again, you can this jump of dimension when you change the rate from when you cross -1, that comes from Fredholm theory, in particular the Lockhart-McQueen theory. So you can study the moduli space using a Dirac operator, which is a Fredholm operator, and it will be a Fredholm operator except when the rate is -1. So you need to remove that point to have finite dimensional kernel, and the kernel of the Dirac operator is the tangent space to your moduli space. So the dimension, to calculate the dimension of your moduli space, you just need to calculate the dimension of the kernel of your Dirac operator. Again, a lot of stuff. For the negative spinor bundle of S4, there are two mathematicians, Clark and Oliveira. Andrew Clark and Oliveira, they wrote down an instanton on this manifold. Again, it means a connection which you can write down in the local coordinates. And there, this is my latest result, the dimension of the moduli space turned out to be 1. So if you look at the expression of the instanton, you will see the a one parameter family, and that's what gives you the one dimensional moduli. So that's it, that's the result. And why you care about the modular space, again, it will give you a lot of, if you only care about the mathematics, it will give you a lot of information about the geometry of those manifolds, and it will have some topological implications, hopefully. Like in the 4-dimensional case, you have the Donaldson invariant, where you just start from the modular space of your 4-dimensional instanton and come up with a topological invariant of 4 manifolds. So this is one direction, and from the physics direction, you want to understand supergravity, where this equation appears as one of 3 equations in the supergravity equation. So these are the 2 aspects of where this result or results of these sorts will be interesting.
So what is this interpretation of the one-dimensional parameter? Does it mean that things become more and more concentrated somewhere? Or?
Okay, so the fact that this is 1 is actually comes from the dilation of the instanton. So it's the this is the dilation parameter. So and here this 1 and 8, this is dilation, this is translation. So in the dimension 8, you can clearly see you can translate it in 8 different dimensions, 8 different directions. So this is where this 8 comes from. This is the dilation deformation, where you are dilating in one parameter, which is here as well, making it bigger, smaller. Here you are just rotating, translating it in various directions. So you can actually explicitly write down the dilation and
so S4 is quite homogeneous. So where is the center?
Right. So it's the negative spinor bundle of S4.
Yeah, but at least you have S4. So where is the center?
Right. So this is the picture. This part is S4. Otherwise, you have a cone over S7. So basically, when we calculate this, we actually calculate this on the cone, and then we using some analysis, we show that it will extend to this S4 part by looking at the curvature and how the convergence of curvature and things like that. So the symmetric property of this S4 actually doesn't come into play. the symmetry of this sphere, that's important. That's a homogeneous space, as I wrote down there, sp2 cross sp1 cosine sp1 square. So this instanton will be sp2 cross sp1 invariant. So that instanton will be invariant under the action of this sp2 cross sp1. Whereas for R8, the instanton, this one will be invariant under S7 action. No, sorry. There, the S7 is actually the homogeneous space spin 7 cosine G2. So that instanton is a spin 7 invariant. And there's the next part of things, that what if it's not spin 7 invariant? That's my current project, that there are no others. So you can ask, are there any instanton which are not spin 7 invariant? Well, there's a story here. Because of this asymptotically conical thing, you can prove that an instanton on this will converge to an instanton on the lower dimensional thing, S7. So you can ask, well, if you start with an instanton on the big thing that's converging to the smaller, an instanton on the small thing, can you find any other example? And my current project involves you prove that this is unique. So the invariant instantons that are invariant under spin 7 or sp2 cross sp1 are the unique one which will converge to a codimension 1 instanton. So there's definitely a symmetry aspect, but that's coming from the symmetry group of those homogeneous.
So are there ways that this modular space becomes infinite dimensional?
Precisely the one I removed, the -1.
Otherwise, it is infinite dimensional.
Yeah, the point is, as I said, you identify the modular space with the kernel of a Dirac operator, and the dimension of the kernel blows up when it's nu equals -1. We call it the critical rate, and they are not worth studying, because if it's blowing up, then you have no control over it.
What is mu smaller than -2? Is mu smaller than -2?
Right. So I did write. Okay. So where does this -2 comes from?
Yeah.
As I said, there's an expression of the instanton, and I said it converges to a lower dimensional instanton on this sphere. So you just like so it converges to, I said. So because of the asymptotic nature of the manifold, you can also ask what's the rate of that instanton. So there's an expression I wrote down involving, so let me remind you very quickly. You have that H, so you pull back that 4 form on x minus k to the cone, and then you compare to the existing 4 form, and that was like order of nu, right? And so for this, you know that your instanton, that's a connection, remember, will converge to some instanton on S7. Consider the simple example. An instanton on R8 will converge to an instanton on S7. So you can do the same. You pull back your instanton to the cone, and then you pull back your connection on the sphere to the cone, and then you compare them, and it will give you the rate of that instanton. Just like that expression, when you work through it, it gave you the rate of the manifold, the rate at which the manifold converges to the codimension 1 manifold. Using that, you can, starting with the instanton, you can also calculate that the rate at which it will converge to the codimension 1 instanton. and this is that rate, -2. Which means you only need to consider -2 to 0. Below that, you don't care about it. The moduli space doesn't exist below.
So this dimension is around the generic connection, right? Or do you have global?
One parameter family of connection, which satisfies the instanton equation, right? It has to be an instanton.
No, you have a claim about the whole moduli.
Yes.
So this dimension is the modular space near the kind of irreducible connection, or
well, this irreducible idea of irreducible connection doesn't. You don't need it on the non-compact manifolds. You can so that all connections are irreducible. Okay, are you? I think you were asking, is it a local thing? Is it a local dimension? No, this is the modular space is global. I'm not saying the modular space of all instantons on R8. Remember, I said modular space of instantons on R8, which converges to an instanton on S7, because I want to have my instanton also exhibit the same asymptotic behavior that my manifold does. My manifold R8 converges to S7 at infinity. So I want my instanton also converts to an instanton on S7 at infinity.
Okay.
So I have that condition imposed on all the instantons I consider in this modulus.
And how many are there on S7?
Okay, that's another thing. As I said, I want to start with the invariant instanton, right? The instantons that are invariant under the spin 7 action. On S7, I also want to consider instanton that's invariant under the spin 7 action. And there we have the best choice, which is called the canonical connection. If you write down the canonical connection of your homogeneous space, that will automatically be an instanton. And S7 being a nearly G2 manifold, remember I said you need to start with a non-integrable manifold. S7 is definitely not a G2 manifold, just like S6 is definitely not a Kähler manifold, not a Calabi-Yau manifold, okay, not a Kähler again. But S6 is a nearly Kähler, which you remember that was a non-integrable exam. Okay. So S7 is definitely not a G2 manifold, it's a nearly G2 manifold. And even in that context, there's a notion of canonical connection. The canonical connections are invariant under the symmetry group, action of the symmetry group. And that's your choice for the instanton on S7. At infinity.
Fixed.
Yeah, that's the fixed one. So yes, usually I do talk about that briefly and do write down this expression, then maybe there will be less confusion, but I was a bit short on time. Sorry about that. Yeah, so all these instanton in this modular space are converging to the fixed canonical connection on S7. That's the best way to put it. And there's a canonical connection on the squash sphere as well, where instantons on bridge will converge to action.